Looks like it's time for a brand new topic here. We're done with torque and circular motion and all the fun of rotating objects for a little bit. And we're on to something called simple harmonic motion. So first off, let's just watch the video here. This is an example of simple harmonic motion. Okay, pretty fancy. I've got my PVC rack for a bowling ball going back and forth here. We can see that rack is curved. So as we get higher up on this curve, the curve gets a little steeper, and so that's directing the ball back toward the middle. Some things that make this simple harmonic motion. First off, there's this point at the middle that ball wants to get back to. Okay, the ball doesn't want anything, but the forces acting on that ball tend to push it back toward that middle point. We call this point the equilibrium point. And then as that ball gets farther away from that point, these forces, they're always pointing back toward that. So if the ball was over here, it'd have a net force going this direction. And if the ball was over here, it'd have a net force going this direction. As we get farther and farther away, since that curve is getting steeper, that force back toward the middle gets larger and larger. So we say that this force that points back to the middle, that's a restoring force. It wants to restore it back to this central position. The restoring force is proportional to the distance from that equilibrium point. As that distance gets bigger, so does the restoring force. That's what makes this simple harmonic motion, and not just repeating motion or periodic motion is the name for that. Now, let's go into a little more detail on this motion, and we'll analyze this by using a graph. So, zoom out a little bit here. We've got a graph, and I noticed that when I watched this video, I timed from this moment right now, when it gets to the highest point off to the left, or off to the right, until it comes right back to that same moment. And I found that that's about 4 seconds to do that. So I laid out a graph here with 4 seconds worth of time set up for us. And then I also made some measurements, not on the video, but actually with the device, and found that the distance from this middle point to the highest point that ball was getting is about 1.5 meters. So I labeled my graph with that. We'll say that anything on the right side is going to be a positive position, and anything over here on the left side of that equilibrium point will be a negative position. Alright, so if we watch this video again, let's start from this point right there. Let's call that a time of 0. So at that moment right there, it's at a position of 1.5 meters. Okay, and like I said, as I timed this, I found that it's about 4 seconds to go all the way to the left and then all the way back to the right. So at a time of 4 seconds, we're back to that starting position. Whoops, a little lower. There we go, starting position again. Okay, let's see where we are in between there. Let's see, after starting there, halfway through, we're as far to the left as we can get. So that would be a position of negative 1.5 meters. And then watching one more time, halfway between far right and far left. At 1 second, we're right here in the middle. Oops, we're right here in the middle at a time of 1 second, right there. And then again at a time of 3 seconds. And so you might have an idea of what this graph looks like already. We need to keep in mind that this is all smooth transitions. Things haven't been happening instantaneously, of course. We're going to have curves, not sharp points. So I'm just going to fit a curve to these points. Let me make that a little smaller. There we go. And then my curve is going to look something like this. And hopefully you recognize this curve. You've seen something like this before. This is a cosine curve. And if I let time go by further, if we watched more of the video, we'd see that this just repeats after this. And it keeps going on like that. So this is a cosine curve. All right, so from this graph, not only are we supposed to be able to make a graph of displacement, but we're also supposed to be able to use this to identify the amplitude, the period, and the frequency of the motion. Okay, so first off, amplitude. Well, we need to know what amplitude means. Amplitude is the maximum distance that our object gets from that equilibrium position. So, based on this graph, we've got our equilibrium position right here, x equals 0. The farthest it ever gets is 1.5 meters in the positive or 1.5 meters in the negative direction. So I could say then that amplitude is equal to 1.5 meters. And you don't need to specify that it's plus or minus 1.5 meters. When you say amplitude, we understand that, yeah, it can be 1.5 meters on either side of that equilibrium position. Second thing we need to be able to do is use this to calculate the period. Now the period is the time to complete one cycle, or the time before this curve starts repeating itself. So if I were on this graph trying to measure that, I could measure that from here to here. After this point, it starts to repeat itself. It goes downhill here, it goes downhill here. That's a repetition. I could measure from here to here. That'd be fine. I could measure from here to here. Those are all periods, and we write that as a capital T. Capital T, capital T. So any point on the curve to the next identical point on the curve, that's the period if we have time on the x-axis here. So in this case, the period is going to be equal to 4 seconds. And then last up, we need to know about the frequency. So the frequency is a measure of how frequently this motion takes place, or how many seconds, sorry, how many cycles, how many complete oscillations back and forth we have for every certain amount of time. Typically the amount of time we use is 1 second. So here, if we've got one more new color, if we've got the time is 4 seconds for one complete cycle, then our frequency is going to be equal to 1/4 of a cycle for every 1 second. Or the way that we would usually write that would be 0.25, just 1/4 divided by 1, 0.25, and instead of cycles per second, we'll use the unit hertz. But hertz just means per second, events per second.